Question 4, this question is about wind energy. It says it is required to design wind turbines for a wind farm for which the following information is available. Total electrical energy output from the wind farm 120 TJ. Now what is this TJ here? Well, the T is a multiplier. It basically means 10 to the 12. It's if we go to our data booklet and we go back a few pages, it says over here it's a tera, so it's 10 to the 12, which is a tera. We also have that the maximum number of turbines for which there is space in the farm is 20, and their average annual wind speed at the site is 9 meters per second. Deduce that the average power output required from one turbine is 0.19 megawatts. So we're looking here at the output in megawatts, and it's for one. Now remember, a watt is a joule per second. Joule per second. And here we are looking at the annual electrical energy output. So that's over a year. So we've got the 120 times 10 to the 12 joules. And we want to divide that by the number of seconds in a year. So we'll take 365 times 24 hours in a day times 60 minutes times 60 seconds. And with that, we'll actually get the energy per second for the wind farm. But we also want to divide it by 20, because there are 20 windmills. And it says over here, deduce that the average power received from one turbine is 0.19 big M watts. Now, remember, that is for mega, that is for 10 to the 6. You can see it on the same page that I showed you before. So let's do this calculation there. Now, remember, in doing this, you must make sure that when you do this division, that you have that in brackets, and also that you make sure that you put this so that it divides into the 120 times 10 to the 12, not just in the 10 to the 12. So it's going to be 120 times 10 to the 12 divided by brackets 365 times 24 times 60 times 60 times 20, close brackets, enter, and I get this value over here, 190258, and then there's a dot in it. But if we look at this, 1 2 3 4 5 6, so 0.19 megawatts. Here we are dividing by a time value and a 20. 20 is no unit, but this is a time, so the answer will be a joule per second, which will be a watts value. So that seems to be correct. Then it says estimate the blade radius of the wind turbine that will give a power output of 0.19 megawatts, and we're told the density of the air is 1.2 kilograms per meter cubed. So we need to go to our data booklet. And remember that this is the formula for power produced by wind. So you've got your power is equal to 1/2 A rho V cubed. We want the radius. Now the power, as we know, is 0.19 times 10 to the 6 is equal to 1/2 times the area, which is pi r squared. We're looking at a wind turbine, so it would be something like this, and that would be the total area, and this would be the radius. This would be what it says over here, the blade radius would be that, times our rho, which is, we know, is 1.2, times by my v, which we saw was 9 meters per second, but it's V cubed. Don't forget that cubed. Easy to do that. So we will obviously then divide by all of this. This is going to the half. Dividing by half is going to be multiplying by 2. And we're going to divide by pi. We're going to divide by 1.2. And we're going to divide by 9 cubed. And we are going to get an answer that is going to equal to r squared. And then obviously we'll take the square root of all that all, and we'll have our r value. So r is going to equal the square root of all of that. So we put that in, the square root, and we're going to open our brackets. I'm going to open a double bracket, I think, just in case. So it's 2 times 0.19 exponent 6, close brackets, divided by open brackets, pi times 1.2 times by 9 cubed, close brackets. I'm going to close brackets again, and you get a final answer that the radius is equal to 11.758, which approximates to be about 12 meters. All of the values here are given. This is to two significant numbers, so I'll put this to two significant numbers here, and that would be that your radius would be about 12. Then it says state one reason why your answer to B is only an estimate. Well, in this formula over here, we're getting the power that's generated from the wind, but there is obviously going to be energy losses. So we're going to get energy losses that we've got. This 0.9 is also an estimate that's taken over data, so the 9 meters per second. This will vary and also may change from year to year. Okay, so that should be fine. And discuss one disadvantage of generating power from wind energy. Well, there's the initial cost, the initial setup. That can take money. There's the land outlay. It usually takes quite a bit of space, land outlay. Some persons don't like the view. They think it's unsightly, doesn't look good. Doesn't look good. And it can also be seasonal. It can change. So it can be seasonal, can change, can vary, depending obviously on the wind speed. It's very important for all these types of energy production. So for each one,